Hello everyone. Under the topic of power system analysis and equal area criteria, in this video, I'd like to talk about what happens following a fault. So, stability under temporary fault. So, what do I mean by temporary fault? Is there is a fault for a small time duration, after which the fault is cleared, and then we are asking the question: is the synchronous machine maintaining stability or not? So let me explain it further with a diagram. So this is the mechanical power input given to the synchronous machine, and I am generating some EMF inside that, and then there is, although I am showing it outside, this is the internal impedance of the synchronous machine. So let's denote it as by Jx. And then this EG, you can think of having some delta naught as the initial angle. And imagine this as your reference bus V at an angle of delta, which I'll assume to be 1 at an angle of 0 degrees. Now, there is a fault here on this bus. So, when the fault is not happening, then some electrical power PE is entering into the grid. So PM mechanical power is entering into the machine, and then here for simplicity, I have not considered in electrical losses because of the resistance and so on. So PM and PE will be equal, and then the power is being transferred here. Now momentarily there is a fault, and when there is a fault the voltage will become zero, because this is a voltage three-phase fault and this is a ground voltage zero, so this voltage will become zero, and as a result the electrical power will become zero. Now we also know that the expression for PE is Eg into V by X sine of delta. So the whatever is the delta at this stage, the delta of the machine is delta naught. At t equal to 0, delta is delta naught, as shown in this figure. But in general, this is the electrical power, and this quantity we are denoting as P max sine delta. So if I draw it as a plot, so it will be some curve like this. So let me draw a bigger figure. So this is PE, which is nothing but P max sine delta. And P max is determined by whatever is EG value, V, X, and so on. So P max is actually EG V by X. Now, how much mechanical power being input? It's all under our control, because this is a infinite bus, and then I'm just generating power and injecting into the bus. So depending on your prime mover, depending on amount of power produced by the prime mover, for example, if it is steam turbine, depending on the amount of steam, amount of PM will be defined. So let's let's say this line represents your PM, which is there, and this x-axis is actually delta, and y-axis is our powers being generated. For stable operation, so we also know the swing equation. So the swing equation is 2 h by omega d square delta by dt square is equal to Pm minus Pe. This is all in per unit. So we had derived this some other time. So for now, take this as the swing equation. So if Pm is more and Pe is less, then the rotor will accelerate. So this delta is the rotor angle, rotor angle with reference to the moving rotating reference frame. If Pe is more than Pm, so this is denoted as Pa. So where Pa is accelerating power. So if, as the name says, if Pa is positive, PM mechanical power is more than the electrical power, then the rotor will accelerate. Otherwise, the rotor will decelerate. So now so we are operating at this point actually because PM is equal to PE and this is a stable point, this is unstable point. So at this point PM equal to PE and then we are operating at time t equal to 0. So here the delta naught is the uh, present steady state angle. Now under these conditions fault has occurred, and when the fault has occurred, so let me write it here. At t equal to 0 and before that, uh, delta equal to delta naught and then PM equal to PE, and then we are operating at stable, operating stable point. Now at t equal to 0 plus, that means just after t equal to 0, immediately, that means that is where we are saying fault occurs. Fault occurs on generator bus. So that is three-phase bolted fault, symmetrical. Bolted fault means the fault impedance is 0. When that occurs, then the entire this PE will become 0, and then we have this is nothing but PM minus 0. So accelerating power is there, the delta will increase. What if the fault is not cleared? So if the fault is not cleared, of course the motor will keeps on, the generator will keep on accelerating and eventually it will lose synchronism and it is not stable. That is not the case. What we are now looking at is at t equal to t1, the fault is cleared. So after a time t equal to t1, the fault is cleared. The question we are asking is the machine stable? Is the generator stable? So there is here at this point I would like to define TC. TC is the critical clearing time. Therefore, if the fault has to be cleared before that time. So therefore, if T1 is greater than TC, then unstable. If T1 is equal to TC, that is critically stable, and then if T1 is less than TC, then it is stable. Therefore, it is very important to clear the fault before this critical clearing time so that I am able to maintain the stability of the system. So, how is the fault cleared? So, we sense the fault current, so there will be a relay here which sends the fault current, and there might be a circuit breaker here which disconnects the generator and so on, that kind of thing. So let's come back to the situation here now. So what I have done is at t equal to 0 fault is created and at t equal to t1 fault is cleared. Now at time t equal to t1, when the fault is cleared, we know that the rotor is accelerating. So therefore let's say this is the place, this is the position where the rotor, the fault has been cleared. So I get this angle as delta 1. So now what about this area? So at this point PM equal to P, but after this electrical power actually is nothing but your x-axis and mechanical power input is y-axis. So this much of variation is there. This much of power is being submitted to the rotor. So therefore this area A1 is kind of proportional to the total energy. So this is accelerating energy. So the rotor is accelerating. That's why I am increasing from delta 0 to delta 1. And at this point, already since I am in acceleration, I am rotating at a super synchronous speed. So even though the fault is cleared, the delta angle will keep increasing, and it will reach to a point which is delta max. But then at delta 1 itself, the electrical power is going to come back because the fault has been cleared. So at this point, electrical power is greater than mechanical power. So for example, you see here electric power is here, mechanical power is only this much. So during the duration of the fault, we are assuming mechanical power is always constant, because in that short few milliseconds time, not much of variation will be there in the mechanical input to the machine. So, since the PE is more than PM, the accelerating power is negative. That means the motor is actually decelerating. So, therefore, it cannot go on forever. There will be some maximum point it will reach, and then after reaching that maximum point, the machine will come back to its original point here after a few oscillations, assuming that the oscillations are going to be damped because of some friction or some losses and so on. Now, so this area will be A2. So the concept here is how much this area A2 can be. So basically this is the energy stored in the rotating mass. That much energy has to be taken out. So equal amount of A2 area will be there such that the energy is taken out of the machine, and finally it will swing and then come back to delta naught. So the question is whether this much area is allowed here or not, available here or not, and to that extent the rotor will overswing and go up to delta max. So this is the equal area criteria. So if A2 equal to A1, then machine will come back to stability. Machine will be stable. All this happened because of this delta 1 I have cleared here. So sometimes if I make a delay in clearing the fault, so I'll show you in another diagram. So let's do this. So I have this as PE, and then this as PM, and this is delta naught. Now, instead of clearing it very early, delta 1, let's say I make some delay. I take long time to clear the fault at this point. So then this much of energy is actually stored in the rotating mass, which results in increase of the acceleration of the machine. Now, how to get back that energy? So at this point, delta 1, I have cleared the fault. At this point, delta 1, I had cleared the fault. So therefore, after clearing the fault, P is coming back, P is more than there, this deceleration is going on. But then I cannot get more area. So the area A2 is actually less than area A1 because I made too much delay in clearing the fault. So because of this, since area is less than A2, the deceleration area is less, acceleration area is more. So machine going on accelerating, and therefore it will lose the stability. So machine loses stability. I say generator loses stability. So there is a particular point that, as I mentioned, critical clearing point when the machine will remain stable. So if I now draw that, so this would be the critical clearing. So this maximum allowed value for delta is that, and this is delta naught. So one thing you should notice here, this is 0, this is pi, and this is the value of delta. So delta naught is nothing but pi minus, delta max is nothing but pi minus delta naught. So this will be later useful. So this gap is equal to this gap because these are coming out same PM here and here. But that is not the point here. The point is the critical clearing. Let me just approximately do that. Let's say there is some particular angle, critical clearing angle. Just a minute. So some critical angle that I would like to find out. So that is what I am going to do in the next video. So such that A1 is equal to A2. What is the delta C? So this delta C is right now unknown. In the next video, we are going to find what is the delta C. Thank you. So hello everyone. So I started off explaining stability under temporary fault, and this is just a continuation video. So far what we have discussed is that in the final case, when area A1 is equal to area A2, so that is the critical case where I have to clear so this is the critical clearing angle. So delta C is critical clearing angle, and associated with critical clearing angle will be critical clearing time, TC. So critical clearing time. So these two quantities I would like to find out. So this is the video for doing that. So in the rest of this I'll do that. So let's take a fresh sheet. So the problem is like this. So the problem is this is PM and this is PE, and currently I am operating at delta naught at time t equal to 0, and then there is a fault, and then the fault is cleared, and at some time here somewhere delta C. So this is the critical clearing angle. So at this angle, so this, as you know, this is angle in delta in pi. So up to here it is pi. So this is the rotor angle, and then this is the power. So at this point I'll have delta max, and then we are looking for a condition where this area is equal to this area. So mathematically I want to find out, given delta naught, what is delta C such that these two areas are equal. So the expression P is P max sine delta. There is just a sine, and then the amplitude is P max somewhere here. So it is not that difficult. We can do it simple derivation to find what is this delta C. So let's do that. What I want to do is just what is A1. So A1 is nothing but this rectangular box. So therefore the area of A1 will be nothing but PM into delta C minus delta naught. So this just gives me the area of A1. I can also integrate PM from delta naught to delta C, which actually comes out to be the same thing. This is area A1. What is area A2? So area A2 basically is that if I give some markings, let's call this A, B, C, D, and let's call this E and F. So the total area, that is E, C, D, F, will be the integration of this P, and minus this PM will be the that area. So if I just integrate uh, delta C to delta max, the PE minus PM. If I integrate this, uh, that will be the area 8 with respect to d delta, of course. So I want to do this now. So and we have all this. So P anyway, this area 2 would be negative if you are actually going as per the this one, that is as per the expression of swing equation. But then here I am just wanting to calculate A2, and then I will equate these two areas. Then I will get the equal area criteria. So what is so from delta C to delta max, I want to integrate. So this curve, that is PE, minus this curve, that is PM. So I get something like this. So P is P max sine delta minus PM, that's all, with respect to d delta. Now, what is integration of this? Integration of sine is minus cos delta, and then P max is anyway constant, that is just a coefficient. So this is delta C to delta max. Similarly, what is integration of PM d delta is nothing but PM into delta, and the delta range is delta C to delta max. Now if I substitute it once again, so P max multiplied by, so I'll get the higher limit minus smaller limit, but then since minus sign is there, so it will be cos delta C minus cos delta max. So I think this is just a basic substitution. So minus PM into delta max minus delta C. So this whole thing is area 2. Now if I look at what is A1, so A1, and if I want to equate this to A2, so A1 is here, PM delta C minus delta naught. So from these two, I can actually cancel out this term. PM minus delta C will be plus, and both sides this will be cancelled out. And then I'll get PM delta naught equal to this one, P max cos delta C minus cos delta max. So here this term is cancelled, so minus PM delta max. So just bear with me, we are almost at the end. So this is unknown, sorry, this is known, this is known, this is known, this is known, and this also known. Only thing that is unknown is delta C. So just I want to write in terms of delta C. So what I get, so this term will go to the other side. So PM delta max minus delta naught, and then it gets divided by P max, and from this will get added. So all of that will be equal to cos of delta C. So everything on the right hand side is known. So just by doing this calculation, I will be able to find out what it is, what the delta C is. So finally delta C is cos inverse of all of this. So this is formula for critical clearing angle. Now just a little bit of more thing is there. Now that you know delta C, I want to find out what is the critical clearing time. So I know delta C, at what time the delta C angle will come, so that I can, before that time I can clear the fault. So for that we need to again go back to the swing equation. So the swing equation is something like this. That is 2h by omega b, or 2h by omega, and this is d delta d square delta by dt square equal to pm minus pe. But during the fault p is absent, so I'll take p is 0, so I'll just remove that. From this, I want to find out what is delta C. So, in fact, delta C is known. At what time does delta C occur? I want to find out. So, just do some manipulation. So, the second derivative of delta is nothing but omega pm by 2h. So, from this integrating, so I get integrating with respect to time d delta by dt. So, second derivative will become first derivative, and this will simply be multiplied by time. So integrating on both sides, this one. By integrating, I get this. There is no constant of integration because this second derivative is actually with respect to stationary, with respect to rotating reference frame. So at this stage, there is no constant term, or the constant term is actually 0 in this case. Now again, if I derive this, so again I'll get delta equal to second again once again derivation of this. So Pm, this will remain as it is. So it will be t square by 2. So integration of t is t square by 2 plus some delta naught, the initial value of delta. So why here the constant is not there is since d delta naught by dt is equal to 0. So at steady state condition, there is no change in the delta naught, or this is constant actually. Anyway, so let's continue. Now in this, if I substitute delta c, then I'll get tc, and delta c is known from the previous case. Now I will find what is tc. So tc is like this. So first delta C minus delta naught will be there, and then to that I will multiply 4h and divide by omega pm, and then square root I'll apply. So this is what will give me the value of critical clearing time. So we have, in this video we had critical clearing angle formula, and then we have the formula for critical clearing time. All of this is based on this particular concept that I have explained. So let's do one example problem on this maybe in the next video, and then we'll get more understanding of how to use this. Hello everyone. So let's continue our discussion on equal area criteria. And then here the case that we are going to look at is with fault resulting in loss of transmission capacity. So in the earlier version of video, what we had seen is there is a temporary fault. This is also a temporary fault where during the time of fault, the entire transmission output is 0. The power going to the grid is 0. Whereas here, the power, there is a partially some loss of transmission capacity there. So let me explain what I mean in the form of this diagram. So this is the generator as you had seen in the previous case. And this is the XD dash of the generator. Or I can actually internally write it here. It's included there, and let's say this is This is a transformer. Let me put a transformer figure. And then there are two transmission lines which are uh, which are connected to the receiving end. So this is line 1 and line 2. So this has direct access reactance XT, and then this has some transformer reactance XT, and this has reactance XL1 and XL2, and then finally this is the infinite bus or the grid. So here it's assumed that it is the voltage is 1 at an angle of 0 degrees. Now what happens if there is a fault at the midpoint of line 2? So the half of the reactance of this line is here, half of the reactance of the line is here. So still some power can flow from the machine to the grid, even if there is a fault momentarily. And then as a result of this fault, there are circuit breakers at the either end of the line. This line is stripped, and after the fault, only one line will be there supplying the power. So that there is a reduction, loss of transmission capacity because of that. So we are going to see such kind of a case. So here the internal EMF is E and this is V, and then X is the total reactance of, that is there equivalently between these two. So as you can imagine, when all the lines are operational, both the lines are there and then transformer, everything is there, you will have one value of equivalent reactance here. So the maximum power that can go from here to here is EV by X. So where this X is the effective reactance connecting the generator to the infinite bus. Now this effective reactance, it will be three values, x1, x2 and x3. So x1 is under normal operation, x2 might be under fault, and then x3 might be after fault. So under normal operation, I have some value of x1. Then during the fault, actually x2, the effective value of x2, it will increase because of this fault, and as a result Pmax will reduce. So we have Pmax 2 as a result of that, and then Pmax 3 as a result of the, after this line is cleared, the this will be again there, so it will be Pmax 3 and Pmax 1 is the normal this thing. So based on this, I'll get three power curves actually. So here the input is mechanical power input and the output is electrical power output. So for P, I'll get three different values. So that is what we are going to see, and that's what is going to explain the equal area criteria. So as usual, this is our delta axis. That is, delta is the torque angle or the load angle or the delta for the machine, and this y-axis is the power. So under normal operation, that is before the fault, so this is my curve. Let's call this curve A. This is P before fault. Then during the fault, the power capacity is reduced. So this is a curve. Let's consider this is curve B. This is P during fault. Now fault is cleared after some time, and then we'll get another curve. This is curve C. This is P after fault. Now in all the cases, my Pmax, my Pm, that is the mechanical input power, that is remaining constant. So let's draw Pm somewhere here. It's a horizontal line like this. So now let's understand. So under normal operation, so at this point, the PM is equal to PE. So therefore, I will have an initial value of delta naught here. Then suddenly fault occurs. When the fault occurs, my power generation reduces. So from this point, reduces to this curve B. I jump from this point A to this point B. Therefore, the mechanical power is more, electrical power is less. So more mechanical power is input to the machine. So machine will accelerate. And as the machine accelerates, the delta keeps on increasing and we move along this line. Then after a while, at some point the fault is cleared. Now when that fault is cleared is somewhere here, let's say. When that fault is cleared at that time, at that instant, let's say the angle is delta 1. So, or delta C, we can call it as a clearing angle or critical clearing angle. When the fault is cleared, my power curve will go back to C. So, I was on A, then from A I jump to this B, and then now here I jump back to point C. So, I put C here and D here. So just to know A to B, B to C. At point C, the fault is cleared, so I go to D. So here, electrical power is more than the mechanical power. So rotor starts decelerating. But still the rotor will overshoot because so far it has been accelerating. And the area that is representing the area of acceleration is this one. So from this point onwards, the rotor starts decelerating and it can achieve maximum area up to this point or earlier to this. But here I have assumed that I'll break the circuit at I'll clear the fault at critical clearing angle. So therefore, this C is here such that I go all the way up to delta max here. Now this delta max is on line C. So from here, this is the area that is, let me give it a different shade. So this is the negative area. So this is my area 2 and this is my area 1. So equal area criteria says that when A1 and A2 are equal, then the machine is going to be stable. And incidentally, what is the stable point? So after the fault is cleared, I am on path C. So this would be the stable point, and this will be the delta F, the final value of delta. So I start at delta 0, then I go up to delta C, fault is cleared, I keep going up to delta max, then I oscillate, and then I keep on oscillating, finally settling back at delta F. That is true. The machine will come back to stability if A1 is less than or equal to A2. If A1 is greater than A2, then unstable. So therefore, it is now the next job is to define what is delta C or calculate what is the value of delta C, the critical clearing angle at which the stability is maintained. So a little bit of mathematics needs to be done after understanding this diagram. So the mathematics is like this. I want to expression for area 1 and I want expression for area 2. So area 1 is pretty straightforward. So because I know this, so let's assume the peak value is P3 max, whereas here the peak value is P2 max. So P1 max we don't require here. So let's do some mathematics on this. So what is area 1? Area A1. It is integration of from delta naught to delta C. So delta naught to delta C. The PM is positive minus this P, this is negative. So that is P3 max sine delta. So this curve is subtracting from that, so I get this area. So this is my area 1. So what is area 2? So area 2 is this area. So the limits are delta C to delta max. So I'll have to integrate something from delta C to delta max. And what I have to integrate is the higher value is the electrical power with P2 max as the amplitude. So P2 max sine delta minus Pm is anyway straight from here to here. So minus Pm. So by the way, this integration is with respect to d delta. This is also with respect to d delta. Now I have to equate these two quantities. So first take a moment, pause a bit if you want, and then see how this area 1 is this and how area 2 is this from the above diagram. So how I can say area 2 is that and this. So once you have this, then the mathematics is straightforward. Let's expand this. Now integration of Pm into d delta is Pm into delta. So Pm into delta minus, so this minus will become plus P3 max. Why minus is becoming plus is because integration of sine is minus cos. So that minus minus will become plus and this will become cos delta. And for this the limits are delta naught to delta C. So this will be equal to Pm into delta naught minus delta C plus P3 max cos of, I'm sorry, this is delta C minus delta naught. This is cos of delta C minus cos of delta naught. Let me add a line in between. So this is area 1 and area 2, let me expand it now. So just look at it. So we get P2 max. Now sine delta integration is minus cos delta and then the Pm integration will be Pm into delta. And then for this the limits are delta C to delta max. Now if I again further expand this, so I get minus P2 max. Now here I have to use cos delta max minus cos of delta C minus Pm into delta max minus delta C. So this is area 2, area A2 and this is area A1 and these two are equal. So when I equalize them, so I can cancel out some terms. So for example, Pm into delta C is here. Here also Pm into delta C is there. So these two terms will cancel out. And then I'll write down the other terms. So Pm into minus delta naught. So this term I have written. Then P3 into this. Cos of delta C. In fact, I'll open this bracket. So plus minus P3 max cos of delta naught. So this is done. Now in this, I'll get minus P2 max cos of delta max. And then this minus into minus will become plus P2 max cos of delta C. Oh, I have to equate this, I'm sorry. So this will be equal to, this whole thing is actually adding to this. So here I get P2 into cos of delta C. Okay, this is plus, and then here this term is anyway cancelled, so minus Pm into delta max. So from this entire equation, I want to solve for cos of delta C. So how to solve for cos of delta C? So you see these two are here, so I can bring these two terms on the left side. So P3 max minus P2 max multiplied by cos of delta C. This I will keep it on the left side. Remaining all terms I will transfer to the right side of the equation. So I'll get this one. So this Pm will go to the right side. So Pm into delta naught minus delta max. Then I'll get this term goes to the right. So it becomes P3 max cos delta naught I think I'm missing a minus sign somewhere. Yeah, so this outside minus sign I'm missing. So here it will be minus, and then for this term, minus into minus it will be plus, and this term will still remain minus. Anyway, I think I have the final expression with me. Let me write it down so that there are no mistakes in this thing. So final expression I'll get cos of delta C should be equal to Pm delta max minus delta naught plus P3 max and cos of delta max minus P2 max cos of delta naught. So this whole thing divided by P3 max minus P2 max. So this from this everything on the right side we know. So we know P3 max, P2 max, we know delta max, we know delta naught. All these things we know. So I can find out what is the critical clearing angle. So finally this is the formula for critical clearing angle. Solving the above, we get this. So this is, and once you get the critical clearing angle, so you can find the critical clearing time as per the process explained earlier. So let's do a numerical problem on this so that we get a better understanding. So for now we'll leave it here. Okay, hello everyone. So in the previous video, we had seen critical clearing angle with the loss of transmission capacity as a formula we have derived. We will use that in a small numerical example that I am going to solve now. So this example is actually example 11.15. This is taken from Power System Analysis Hadizadeh textbook. So let's look at the problem. So the problem is something like this. There is a generator here whose direct axis reactance is 0.3, followed by a transformer whose reactance is 0.2, and then two transmission lines each having 0.3 per unit reactance, and finally connected to the infinite bus whose voltage is 1 at an angle of 0. It is also given that the total power, that is the complex power, is nothing but the active power and reactive power. So is 0.8 plus J 0.074 per unit. So this much of power is being delivered to the infinite bus from the generator through two transmission lines and this transformer and so on. The question that is asked is, there is a fault at the midpoint of this particular transmission line. So prior to the fault, there is a steady power flow of this much. and then there's a fault which is occurring, and due to this fault there will be a reduction in the power flow limit, and then when the fault is cleared, this particular circuit breaker and this circuit breaker are open circuited, so thereby this entire line is isolated, and now the transmission network is only one single line, so we have a still some power flow going on. So the maximum power transfer limits in each of these cases, that is before the fault, during the fault, and after the fault, will be different. So that's what we'll have to calculate in this. So finally, the question that is being asked is determine the critical clearing angle. So when this fault occurs, the rotor of this generator accelerates, and then at how much angle we should isolate the fault so that the machine still remains in synchronism with the infinite bus. So let's get started with that. So first, how do we solve this? So first we start by finding the current. So the current is complex power conjugate divided by voltage conjugate. So here the complex power is this one. So 0.8, and because it is conjugate, I am putting minus 0.074. So this minus I am taking because of this conjugate. Then voltage here is just 1. So since angle is 0, so the conjugate also doesn't matter. So finally I am getting 0.8 minus j 0.074 per unit. Now I have the current. Now look at the total impedance between this and this. So first there is a generator. Generator itself has the internal impedance of 0.3, that is internal reactance. Then there is a transformer whose reactance is 0.2. Then I have two lines, 0.3 and 0.3, which are in parallel. So 0.3 and 0.3 in parallel would be 0.15, and then total reactance XT will be 0.15 plus 0.2 plus 0.3. So this would be 0.65 per unit. So now I have total reactance. So from this I can find out, so I know the total current and total reactance. So from that I can find out what is the E dash. So E dash is nothing but the receiving end voltage plus the drop. So that is J into X total into I. So what is this? So I know the voltage is 1, and then the X is 0.65 J, and then the current is this one, 0.8 minus J 0.074. So once I do this calculation, so I will get the value of E1. So this value turns out to be 1.17 and at an angle of 26.387 degrees volts. So this is after converting into polar, I am getting like this. So the magnitude of E1 is 1.17, and then the angle of E1, that is this one, 26.38. So that means delta naught is 26.38 degrees. You can approximate to 26.4 degrees. And E magnitude is this. So now first I want to determine what is the Pmax1. Pmax1 is the maximum power that can be transferred when both the lines, the system is under normal operation. So that is EV by X. So E is 1.17 I know, and V is 1, and X is 0.65. So these are all magnitudes. So this turns out to be 1.8. What is Pmax2? So Pmax2 is when the line is under faulted conditions. So this is maximum power limit under faulted conditions. So what happens during the fault? If I go up, so the fault is at the midpoint of this. So in other words, the fault is at the midpoint of this. So let me redraw this diagram now. So I have the generator, its internal impedance is J point 0.3. I'll just skip the J here, and then zero point 0.2, and then I have one line is zero point 0.3, and then the other line is 0.15, and this is a midpoint, and then 0.15. So this point is connected to the ground, and then the receiving end directly is your final bus. So under these conditions, so here I have EMF E, and then here I have the infinite voltage, infinite bus voltage, that is 1.0 angle 0 degrees. Now I want to know what is exactly the resistance between this machine and this one. So here you see this point is like a star connection. So I'll further simplify it. So this is E, and then I have a star connection of 0.5, and this side is 0.3, and this side is 0.15, and also there is a 0.15 here, and then finally I have the infinite bus. So this is where the fault has occurred. So this is my V infinite. Now this star connection I can convert into delta. So when you convert into delta, so this particular reactance, whatever comes between these 2 points, will be something like this. So 0.5 plus 0.3 plus 0.5 into 0.3 divided by 0.15. So that will be X total, that is between this point and this point. So if I say A and B, so between A and B, this will be the match. So this is basically star to delta conversion. So this value 0.5 plus 0.3 plus 0.5 to 0.3 by 0.15 turns out to be 1.8 per unit. So if this is 1.8 per unit, I can just redraw the drawing now. So this is E. There will be some impedance which we did not calculate. This is 1.8, and then this one I know is 0.15. This one is not required here. This is 1.8 per unit, and then finally I have the V here. So this is what matters when calculating the maximum power transfer capability. So that is P max will now be EV by X, which is 1.17 into 1 divided by this one, 1.8. So this is 0.65. So this we are denoting as P max 2. Next we have to find out what is P max 3. P max 3 is under after fault conditions. So when the fault is removed, the system is something like this. So this particular line which is there, this line is open circuited. Let me just show it as open circuit. So the circuit breakers on both sides open, and then this fault is isolated. So this is 0.3, this is 0.2, and this is 0.3. So this is E and this is V. So the total impedance now is just a series addition of this. So the total impedance is 0.8 per unit. So therefore P max 3 I can find that is EV by X. So that is 1.17 into 1 by 0.8. So this value will be 1.4625 per unit. So I have now three values. So let me diagrammatically show them so that it will become more clear. So this is under normal operations. This is P1. So the maximum value here, P max 1 will be equal to 1.8 per unit. This is under normal operation. Now, if I have a fault under faulted conditions, this is my Pmax. So the height of this will be, I'll just write it here. Pmax 2 is 0.65. That's what we calculated. And then the third curve that we calculated, it will have, this is after the fault is cleared, this point, that is P max 3, that is, we just calculated 1.46. And under normal operation, if I go to the question that is given, so the active power that is going is 0.8, that is given in the question. So because active power is 0.8, so at 0.8 I draw a line. So this is 0.65, so 0.8 line will be somewhere like this. Let me use a different color. So this is P mechanical 0.8, because electrical power, mechanical power will be matching. And we already calculated this angle, that is, this angle is delta naught. We already calculated that. So what is delta naught? So if I go up, so 26.387 degrees. 26.387 degrees. So when the fault occurs, so this is before fault, this is during fault, and this is after fault. Okay, so when the fault occurs, at the time I am operating at this point, at the time I jump to this point, and then mechanical power is more than electrical power, so the rotor will accelerate. So I keep accumulating this area and I'll keep moving towards the right. So after some angle, the fault is cleared. So let's denote this as delta C. So here I am assuming that the critical clearing angle is delta C. So that's what I want to find out. This is unknown. So then I'll directly jump to this point from this point, because now I am on this curve, because fault is cleared. This red curve will be what is there. So mechanical power is still 0.8, electrical power is almost here. So this area will be my decelerating area. And when these two areas are matching, so maximum it will swing up to here. So that is delta max. And then it will come back. So delta max actually I can find out. So how to find delta max? Because I know this curve, so this is 0.8 and this point is 1.46. So here it is. So from 1.46, 0.8 I can do sine inverse. Then I'll get this angle that I have to subtract from 180. So first let me start doing that. So delta max will be 180 degrees minus sine inverse of 0.8 divided by 1.4625. So this one I'll get something like 146.8 degrees. Or if I convert into radians, it will be 2.56 radians. So that is this delta max angle. So now I know, so this is 146.8. So I know this angle, I know this angle. So this angle I have to find out. And then I also know P1 max, P2 max and P3 max. So then we can actually solve it. So if I just quickly refer to the previous video which I have done. So this is the formula. So this is critical clearing angle. So here everything I know. PM I know. Delta max. PM is zero point 0.8. Delta max we just calculated. This also we know. P3 max, P2 max. All these things we know. So just by substituting all this, I'll be able to find the uh, solution. So let's do that. So I'll get cos of delta C equal to, it might help if I copy the formula. So let's try to do that. So here is the formula. So from this, I'll find out cos of delta C equal to, so PM is 0.8 given in the question, and delta max, in radians it is 2.56 radians, here I mentioned that, minus delta naught. Delta naught also I have to give in radians, so that is 0.46 plus P3 max we just calculated, that is 1.4625, then cos of delta max. So cos of delta max, so cos of this 2.56 radians minus, so this minus is there. P2 max is 0.65. This is the maximum power during the fault, and then cos of delta naught, so 0.46. And this whole thing divided by, excuse me, this whole thing divided by P3 max is 1.4625 minus P2 max is 0.65. And if you calculate this, the answer turns out to be minus 1.53. And then, so from that, this is cos inverse of minus 0.153. So that will be 98.8 degrees. So this is the critical clearing angle. That means if I clear, so this one we solved it 98.8 degrees. So if I clear the fault before the rotor reaches 98.8 degrees, then the synchronism is maintained. Otherwise, synchronism is lost. So basically, this is a numerical example to show how to use the equal area criteria to determine whether the machine will be stable or it will be unstable. So I hope you got something from this solved example. So so with this we kind of conclude our study of equal area criteria. Thank you.